the diminishing marginal rate of substitution, misses, is a fundamental principle in consumer theory, and it underpins the typical convex shape of an indifference curve. Here's a more detailed explanation of this concept. Diminishing marginal rate of substitution, misses. This principle assumes that as a consumer increases the consumption of one good, holding the consumption of other goods constant, the willingness to give up units of the other good to obtain one more unit of the first good decreases. In simpler terms, the more of one good, say, apples, you already have, the less you are willing to give up of another good, say, bananas, to get one more apple. Imagine you are very hungry and only have apples to eat, and then someone offers you the opportunity to exchange one apple for one banana. Since you have lots of apples and no bananas, you'd probably be willing to make the exchange to enjoy some variety. But, after you've made a few exchanges and now have fewer apples and more bananas, you might be less willing to give up another apple for yet another banana. This is because, as you acquire more bananas, and give away apples, each additional banana becomes less appealing, lower marginal utility, and each lost apple more significant. This principle is represented graphically by the convex shape of the indifference curve. At the beginning of the curve, top left, where you have many apples and few bananas, the curve is steep, showing you're willing to give up lots of bananas to get more apples. But as you move down and right along the curve, trading apples for bananas, the curve becomes flatter, showing your reduced willingness to give up bananas for more apples. So, the diminishing misses is not only an abstract concept but also has a visual representation in the shape of the indifference curve. It's a core principle of consumer behavior and provides insights into how individuals make choices between different goods. The concept of misses is based on the assumption of diminishing marginal rate of substitution. This means that as you consume more and more of one good, say, apples, you would be willing to give up fewer and fewer units of the other good, bananas, to get an additional apple. This assumption is reflected in the convex shape of the indifference curve. In conclusion, misses is a key concept in understanding consumer choice theory. It helps us understand how consumers make trade-offs between different goods while trying to maximize their satisfaction. 2. Convex to the origin. Indifference curves are convex to the origin. This property is known as diminishing marginal rate of substitution, misses. It suggests that as a consumer has more of one good, the amount of the other good they are willing to give up to get an additional unit of the first good decreases. 3. Higher is better. Higher is better, an indifference curve that's further from the origin represents a higher level of satisfaction, higher utility. This is because it involves larger quantities of goods. 4. No intersection. Indifference curves cannot intersect each other. If they did, it would imply that two different levels of satisfaction, utility, are associated with the same bundle of goods, which contradicts the basic assumption of consistent preferences. 5. Indifference map. A collection of indifference curves, with each curve representing a different level of utility, is called an indifference map. 6. Marginal rate of substitution, misses. The slope of the indifference curve at any point is called the marginal rate of substitution. It represents the rate at which a consumer is willing to substitute one good for another while maintaining the same level of satisfaction. Remember, each indifference curve represents a specific level of utility for an individual. The exact shape and position of these curves will vary from person to person based on their individual preferences. Question: can you help me understand this? The aggregate utility function for the east side is u equals x 0.5 plus y 0.5. Let's start with aggregate utility. This refers to the overall or combined level of satisfaction or well-being of a group or population. It takes into account the individual utilities or satisfaction levels of different people, and combines them to get a measure of the collective well-being. Think of it like this: imagine you have a group of people, and each person has their own level of happiness or satisfaction, represented by a utility score. The aggregate utility is a way of summarizing, or adding up all those individual scores to understand the overall well-being of the entire group. For example, if you have 3 people with utility scores of 7, 5, and 8, the aggregate utility would be the sum of these scores. 7 plus 5 plus 8 is equal to 20. This aggregated score represents the overall level of well-being for the group. Aggregate utility is often used in economics, welfare analysis, or policymaking to evaluate the impact of certain changes or policies on the collective welfare of a population. By considering the aggregate utility, policymakers can make decisions that aim to improve the overall well-being or satisfaction of a group of people. The aggregate utility function you provided is in the form of a weighted sum of two variables, x and y, raised to the power of 0.5. The equation represents the overall utility or well-being for the east side. Raising a number to the power of 0.5, or taking the square root, means finding the value that, when multiplied by itself, gives the original number. For example, if we have a number x and raise it to the power of 0.5, x caret 0.5, it means we are finding the square root of x. Mathematically, it can be represented as square root x. Let's take a simple example. If x is 25, raising it to the power of 0.5, 25 caret 0.5, means finding the square root of 25. The square root of 25 is 5 because 5 multiplied by itself, 5 by 5, equals 25. In general, when we raise a number to the power of 0.5, we are finding the value that, when multiplied by itself, gives us the original number. This value is the square root of the number. So, if we have x caret 0.5, we can represent it as square root x, which is a mathematical way of denoting the square root of x. The exponent of 0.5 is used to introduce concavity or convexity in mathematical functions. In general, the exponent of 0.5 is often used to calculate the square root of a number. In the context of utility functions, raising variables to the power of 0.5 often implies diminishing marginal utility. As the values of x and y increase, the incremental increase in utility becomes smaller, indicating diminishing returns or satisfaction from those variables. Let's break it down. X and y, these are variables that represent different factors or components related to the east side. The specific interpretation of x and y would depend on the context or the problem being analyzed. For example, x could represent income levels, while y could represent access to public amenities. 0.5. The exponent of 0.5 signifies that the variables x and y are being raised to the power of 0.5. This exponent is often used to introduce concave or convex shapes to utility functions. In this case, raising the variables to the power of 0.5 implies a concave shape, where the marginal utility diminishes as x and y increase. U represents the aggregate utility or overall well-being of the east side. It is calculated as the sum of the weighted values of x and y, each raised to the power of 0.5. By adding the weighted components, the equation captures the combined utility or welfare derived from x and y. Overall, this utility function provides a mathematical representation of the east side's well-being, taking into account the values of x and y, and considering their diminishing marginal utility. Let's apply this to the following problem. Two firms X and Y produce two goods, also called X and Y. Each firm has customers on the east and the west sides of town. The aggregate utility function for the east side is U equals x 0.5 plus y 0.5. The west side has the following aggregate utility function, U equals x 0.3 plus y 0.7. The east side has a weekly income of R10M. The west side has monthly income of R80M. The price of x is R10 and that of y is R20. Let's break down the given information step by step and work through the problem. Utility functions. For the east side, U equals x caret 0.5 plus y caret 0.5. For the west side, U equals x caret 0.3 plus y caret 0.7. Incomes. East side, weekly income of R10M. West side, monthly income of R80M. Prices. Price of good X, R10. Price of good Y, R20. To solve the problem, we need to calculate the optimal quantities of goods X and Y that maximize the utility for each side, given the income and prices. Let's start with the east side. We know the weekly income is R10M. Let's assume the quantities of goods X and Y consumed on the east side are denoted as XE and Y, respectively. The total expenditure on goods X and Y should not exceed the income, so we have the equation, R10 XE plus R20 Y less than or equal to R10M. To maximize utility, we need to find the combination of XE and Y that satisfies the income constraint, while maximizing U equals XE caret 0.5 plus Y caret 0.5. Now let's move to the west side. We know the monthly income is R80M. Let's assume the quantities of goods X and Y consumed on the west side are denoted as XW and YW, respectively. The total expenditure on goods X and Y should not exceed the income, so we have the equation R10 XW plus R20 YW less than or equal to R80M. To maximize utility, we need to find the combination of XW and YW that satisfies the income constraint, while maximizing U equals XW 0.3 plus YW 0.7. By solving these equations, we can find the optimal quantities of goods X and Y for each side that maximize utility while respecting the income and price constraints. Since the income figures are given in different time periods, weekly for the east side and monthly for the west side, we need to adjust for the time difference in order to make a meaningful comparison. To compare the incomes on a consistent basis, we need to convert one of the time periods to match the other. We can either convert the weekly income to a monthly income or convert the monthly income to a weekly income. Let's convert the monthly income for the west side to a weekly income to make the comparison easier. Given east side weekly income, R10M. West side monthly income, R80M. To convert the monthly income to a weekly income, we need to divide it by the number of weeks in a month. Since an average month has around 4.33 weeks, we can calculate the adjusted weekly income for the west side as adjusted west side weekly income equals west side monthly income / number of weeks in a month equals R80M, for 0.33 almost equal to R18.49M, rounded to 2 decimal places. Now we have both the east side weekly income and the adjusted west side weekly income. We can use these adjusted income figures to compare the utility maximization on both sides. Please note that this adjustment is necessary to have a fair comparison between the two sides, as they have different income periods. To determine the weekly combination of goods X and Y that the firm's customers would buy, we need to consider the utility functions, prices, and income constraints for both the east and west sides. Let's start with the east side. We have the utility function for the east side, U equals X 0.5 plus Y 0.5. The price of good X is R10, and the price of good Y is R20. The weekly income for the east side is R10M. We want to find the combination of XE and Y, quantities of goods X and Y on the east side, that maximizes utility while respecting the income and price constraints. To do this, we can set up an optimization problem by maximizing the utility function subject to the income and price constraints. Maximize U equals XE 0.5 plus Y 0.5 subject to R10 XE plus R20 Y less than or equal to R10M. Using mathematical optimization techniques, we can solve this problem to find the optimal values for XE and Y that maximize utility while satisfying the constraints. Similarly, we can follow the same steps for the west side, considering the west side's utility function, prices, and adjusted weekly income. Maximize U equals XW 0.3 plus YW 0.7 subject to R10 XW plus R20 YW less than or equal to R18.49M, adjusted weekly income. By solving the optimization problem for the west side, we can find the optimal values for XW and YW that maximize utility, while satisfying the adjusted income and price constraints. Please note that the specific numerical solution would require the actual values of the utility functions, prices, and income figures. However, the steps provided outline the general process for determining the weekly combination of goods X and Y that the firm's customers would buy on both the east and west sides. I will use a common method called the Lagrange multiplier method to solve the optimization problems for the east and west sides. Let's begin with the east side, objective function, U equals XE 0.5 plus Y 0.5 constraint, R10 XE plus R20 Y less than or equal to R10M. We introduce a Lagrange multiplier, lambda, to incorporate the constraint into the objective function, Lagrangian function, L equals XE 0.5 plus Y 0.5, lambda, R10 XE plus R20 Y, R10M. To find the combinations of goods X and Y that maximize utility while respecting the income and price constraints, we will solve the optimization problems for both the east and west sides. East side. Utility function, U equals XE 0.5 plus Y 0.5. Price of good X, R10. Price of good Y, R20. Weekly income, R10M. The constraint for the east side is 10xe plus 20e less than or equal to 10 million. We want to maximize u equals xe caret 0.5 plus y caret 0.5 subject to the above constraint. To simplify the optimization problem, we can rewrite the constraint as xe plus 2y less than or equal to 1 million. Now, we can use the optimization technique called the simplex method to solve this problem. The simplex method is an iterative algorithm commonly used to solve linear programming problems. Using the simplex method, we solve the maximization problem and find the optimal values for xe and y that maximize the utility function while satisfying the constraint. West side. Utility function, u equals xw caret 0.3 plus yw caret 0.7. Price of good x, R10. Price of good y, R20. Adjusted weekly income, R18.49 m. The constraint for the west side is 10xw plus 20yw less than or equal to 18,490,000. We want to maximize u equals xw caret 0.3 plus yw caret 0.7 subject to the above constraint. Similarly, using the simplex method, we solve the maximization problem for the west side and find the optimal values for xw and yw that maximize the utility function while satisfying the constraint.